Now for third problem, we use the cast iron. Then the new cast iron, for new cast iron, this is the roughness coefficient. So I'm just showing this one. I will not just come back here again. Okay. So this is how we can get the the properties from this table. And in different books, this values it's little bit different. You will see it's 0.25, but when I solve it, I use it is 0.26. So it doesn't matter. Okay. And this is the Mori diagram. It will make your life complex. You will see two different things we need. One is the Reynolds number, other one is epsilon over d. So this epsilon over d is the ratio of the relative roughness and the diameter of the pipe. Okay, so Reynolds number, we know different formula, guys. This is one formula. Other formula, it could be B D over nu. So you know the difference between this. This is kinematic viscosity. This is dynamic viscosity. We discussed it in first couple of weeks. Yep. Yeah, so that's the mu, this is the dynamic viscosity. And this nu, this is kinematic viscosity. And you know how we get it? Rho density over dynamic viscosity. This is actually of the the materials, the water or air, whatever you are using. It is actually the kinematic viscosity. You look here, this rho over, it is called mu, Greek symbol, it is equal nu. So this is, let me say, this is dynamic, and this is the kinematic viscosity. Yeah. So this is the same thing. If we use the kinematic viscosity, then we do not need to use density anymore. Okay. So I believe you know it. We used it in week 2, week 3. So now, what we can understand from this diagram is we need to use the we need to know the epsilon over d and the Reynolds number, and when we will have these two values, then we will get the friction factor from here, right? But we're going to solve on questions where we only know one value. We don't know Reynolds number. So that's really confusing, complicated thing. So let's start with the problems. So let me tell you how you will get the friction factor from this problem. Let's say, for example, you calculated the epsilon over d is 0.001. Suppose, just for understanding, okay? And this is our Reynolds number. Let's say 2.4 into 10 to the power 5. Just for an example. So we'll see if we draw a line like this. If we draw a line like this, we see it intersects the point here. So this is actually, if we go this way, then we can see, okay, this is the value 0.02. So we say this is the friction factor value. But still it has a lot of confusions. I will explain it. And today we have limited time due to 3 problems. But tomorrow, what I will do is I will upload a separate video on this diagram, like how to use this Moody diagram, okay? Then you can get better, clear understanding. I already told one of my tutors because I'm so busy. So I said, please make a video. So he said he will. If he don't, then I will do it, okay? So here, actually, this is how we will use the Moody diagram. Now, the question we are going to solve, we only know this epsilon over d, but we don't know the Reynolds number. Then what we will do, guys, okay, so just concentrate. The problem we are going to solve, we know only epsilon over d. We don't know Reynolds number. That means we'll not get the F, but we need to solve this problem. So then what we will do, we will make some assumptions here. Let's say this is our value. So we will get a corresponding, friction factor value. and then we'll do some trial and error calculations, and we'll see whether our assumptions and the realistic value is close enough or not. So this is some sort of validation, and it will kill a lot of our time. So, but we need to understand this, because this is you need to do in real life. When you will work with industry, you will see you need to do these sort of things. So this is the question 3. You look, we have the reservoir here. This is the height, the height, it is given 5 meter. This height is 5 meter. We have got the pump here. So this is the pump. This is the inlet pipe. This is the outlet pipe, or the discharging pipe. This inlet pipe length L1 is 1000 meter. This outlet pipe length is 500 meter. This diameter is 0.220 meter, and this is 0.180 meter. Okay, water temperature is 20 degrees centigrade, and I think that's all informations. Here it says we need to determine the water flow rate and the pump power when cavitation is about to begin in cast iron. So we'll calculate the flow rate at first. So for better understanding, I will define this is point O, okay? This pump, it is point I, and this exit 5 is E. So I use these notations here. This is O, this is I, this is E, okay? So now, in this case, the question didn't say that, okay, it is, you know, ideal flow or whatever, anything we didn't mention in this question. So that means we need to actually consider the loss, the friction loss, you know, the head loss. So if I apply the energy equations here from point 0 to I, okay, so there will be no head loss, but we will have the friction loss. Okay, so we don't have the pump heads here, but we have the, you know, for between point 0 to I, we can write, let's say we're writing the energy equations. So the energy equations, we can say, you know, P O rho G VO square 2G ZO Pi rho G VI square 2G ZI plus the loss, the head loss. Here, in the state of head loss, I will just directly write it down like this. F1 L on D on, you know, VI square over 2G. So this is, if you ask me how you got this formula, I showed you the major and the minor loss formula at the very beginning of this lecture, and we discussed it last time. So this is the loss for this pipe. That means the inlet pipe. F1 is the friction factors. Look, we have the water here. This is the water at rest. We can say the water velocity is 0. Right? At this point, do we have any elevations? No. We can say Z equals 0. But the rest of the thing, it's not 0. Here, we have the pressure is, we can say this is the atmospheric pressure or the barometric pressure here. We have the pump cavitation will happen here. So this is the vapor pressure. So what we can do, guys, we will substitute all the values. P naught, you can say 101, 325, or in some cases we can use 300. It's okay, we all get more or less same solutions. The density is 1000, gravity 9.8. It is equal, you know, Pi, it is 2340 Pascal. Density is 1009.8. BI, we don't know. VI square over 2 into 9.8 plus Z1 is 5 meter. It should be 5 meter here. So Z1 is the elevations here at this position. So this is the elevations from point O to I. Plus this is 5 meter. Okay, this is 5 meter. We have limited space here. So plus F1. We don't know F1. L1 is 1000. Diameter is 0.220. BI square we don't know, and this is 2 into 9.8. Sorry, it is, we have actually, the limited space here. So I'm telling you can write it down. This is F1, 1000, this is the length. This is the diameter 0.220 into BI square. This is BI square over 2 into 9.8. Okay, so this is BI square over 2 into 9.8. So next time I will try to write it down and I will make more spaces. Okay, so if we simplify this, guys, you look closely, we have two unknown here, V1 in the pump inlet velocity and the friction factor. Okay, the thing is, we need the the water flow rate. Okay, so flow rate means, I think I missed something initially. I should mention, because why I am doing this, we are going to calculate the water flow rates. So the flow rate means the velocity into area, right? So here flow rate means actually the pump flow rates, the flow rate at the pump inlet. Okay, so we need the pump inlet velocity and the area. So we don't know this VI, that's why we are just doing these calculations. You understand what I mean? So for the first question, we need the water flow rate. Let me write it down here. So the flow rate at the pump inlet, it should be VI into the area. So we don't know VI. So that's why actually we're using the Bernoulli equations for this point O, this is point I, this is E. Now we have got these expressions, guys. I will write it down clearly. If we simplify that one, okay, the previous equations, then we'll get it like this: BI square into 1 over 4.545 F on L. Okay, sorry. All right, it is 544 F on, it is equal 99.9. Due to some outstanding digits, sometimes you may get it is 99, but it's okay. Okay, so it is 99.9, but if you get 99, that's okay. So we have, look, when we just simplify these expressions in calculator, we'll get it like this. So we have two unknowns. One is this VI and the FI. But we're talking about the flow rates. Flow rate means the velocity and the area. So we must need the velocity. And if we don't have the velocity, then we cannot solve these questions. So we need the pump inlet velocity. And if we want to get the pump inlet velocity, then we need the friction factor. You look here. We need this friction factor now. Now, for the cast, our material is new cast iron. Okay. For new cast iron, the epsilon is, we see 0.26 the millimeter. So then the relative roughness, the relative roughness, epsilon over D. So this is 0.26 millimeter, and we had the diameter of the pipe is 0.220 millimeters, so it's 220 millimeters. So it will cancel it out. So this value we will get 0.00118 maybe something, or you can say 0.0012 epsilon over d. So this is, look, this is we got from the tables I showed you earlier, and this is the diameter of the pipe, so diameter of the inlet pipe, and we got this value. Now if we want to use the Modi diagram, guys, then apart from this value we need the Reynolds number, right? The Reynolds number is the velocity, diameter, and kinematic viscosity. This is the definition of the Reynolds number. So the velocity means this is actually the velocity of the pump inlet, which we don't know. We are looking for that. So this it's complicated scenario now. We have these expressions with two unknown, vi and fi. So we need fi to get the velocity, and we can get it from the Modi diagram, but we need epsilon over d and the Reynolds number, but we cannot calculate the Reynolds number because we don't know this velocity. Then how we can solve it? You understand what I mean? So these two values we need, but we don't have this Reynolds number. Now what we will do, guys, I will just go back to the Modi diagram. Our relative roughness value, we got 0.0012, right? We will find out a closest roughness, relative roughness value. What we have here is this 0.001. You see, this is the closest one, whatever we have here. This is 0.001. We will just follow this line, and if we follow this line, we got the friction factor is 0.02. So now we will use some assumptions that F1 is 0.02. You understand what I mean? Otherwise, we do not have any other ways to solve these questions. But we are using these assumptions. We will definitely validate it later on, whether our assumption is correct or not. So, what do you mean what, Vatan? Yeah, so you said what? I didn't understand your question. Please unmute your mic and tell me. Could you please just unmute your mic and ask the question, because it just put a question, answer, because I actually need to know your question clearly. For final exam? No, don't worry about it. Okay. But we need to learn it. We need it in real life. Because when you will work with an industry, you must need to use the Modi diagrams, if it is something like that. So we're running on subject, and I must need to learn some, the basic tools, knowledge that you need in your real life. If you don't know, then you will be, oh, what is this? I did fluids mechanics, and then you will remember me with some bad comments maybe. And for God's sake, you just spoiled our lives. So I must need to teach you, okay? So don't worry about that. Okay, so look, you didn't ask the question, but what I said, we got the relative roughness is 0.0012. We don't know the Reynolds number. That means we can't get the friction factor from here. So we are using some assumptions. It is called the trial and error method. You must need to learn as an engineer, and in that way you will do the optimizations. So this is the closest value. We got 0.001, and we took the corresponding the value, which is 0.02. So we said, okay, this is the F1. So we assume that F1 it is equal 0.02. Okay. So now I believe you cleared that why F1 equal 0.02. So when we are putting F1 0.02 in these expressions, let's say this equation is number 1. we just put a number for these equations. So we can write from equation 1, vi square into 1 plus 4545 into 0.02 equal 99.9. And if we solve this bi, the velocity, it will be 1.043 meter per second. So you look here, by using the assumptions, we got the velocity for the pump inlets. Okay, but there is a major questions whether our assumptions is correct or not, because the relative roughness we use, it was 0.0012 and we are using the value for 0.001. So we'll now validate our assumptions. So now you have the velocity, so you can now calculate the Reynolds number, isn't it? So now calculate the Reynolds number. Then Reynolds number, it will be V d over nu. It is called nu, Greek symbol. So V, that means Vi, it is 1.043, diameter is 0.22, and for 20 degrees centigrade temperature, the kinematic viscosity is 1.10 to the power minus 6. So we'll get it is 2.3 and 10 to the power 5. That's the Reynolds number. Okay, there's the Reynolds number now. And we already have the epsilon over d, it is equal 0.0012. So we have these two value now, epsilon over d and the Reynolds number. Okay. It should be in the appendix. Yeah, it's actually here. We have the water. So for water, we have all the values here. We're using it for, I think, 20 degrees centigrade temperature. So you just need to get it from, I didn't put it here, but it's from previous weeks, like week 1, 2, 3, okay? Yeah. So you will get it from there. So that's why I didn't put it here. But if you want, guys, then I'll put it in this slide and I'll upload it later on, okay? Yeah, so this one, we have got this epsilon over d and the Reynolds number is this. So by using these two values, okay, from the Moody diagram, from the Moody chart, we will get the friction factor is 0.0215. You know, I will, as I mentioned earlier, I will upload on video. Let me check the time where we are now. Okay, it's exactly 1 hour. So by using this two value, we got the F equal 0.0215. Now, if I use this value again in these expressions, let's say equation, we mentioned earlier the equation 1, which is bi squared 1 over 4545 upon 99.9. Now I will use this value again, 4545 into upon equal 0.0215 into 99.9. Then vi, it will be 1 meter per second. See, I'm doing again and again. It's a bit confusing, but this is actually the process, like the trial error. Like you see, initially we got the velocity from the assumptions. Then by using that value, we calculated Reynolds number. And this Reynolds number we used from Moody diagram, we got this friction factor. Now we are using this friction factor to calculate the velocity. We got this velocity. Now I will calculate the Reynolds number again by using this velocity, like V d over nu, which is, which is 1, diameter is 0.22, it is 1 into 10 to the power, I think, 6. So we got, it is 2.2 and 10 to the power 5. That makes some differences. Now I will explain it. You see here, this Reynolds number is 0.2, 10 to the power 5. And previously, we had the Reynolds number 2.3 and 10 to the power 5. Right? So that's not same. So that means is our assumptions incorrect? Yeah. So in general sense, the answer is yes. So if we look about these values, like we got two different values, but the Modi charts, you look here, this is in log scale. You know what is log scale? Yes. So log scale means it's kind of the not equal subsections in the x-axis. You look guys here. Just try to understand. This is 10 to the power 5. Okay, the Reynolds number. We're talking about the x-axis. This is 10 to the power 5. This is 10 to the power 6. Okay. This value, this is this dotted point. This is 2 and 10 to the power 5. Okay. This is 4 and 10 to the power 5. So that means from here to here it is just 2. But we have how many sections? 1, 2, 3, 4. 4 subsections. So that means we can say this is this point, this is 2.5. This is 2.5 and 10 to the power 5. This point is 3 and 10 to the power 5. This is 3.5 and 10 to the power 5, and this is 4 and 10 to the power 5. You understand what I mean? So what we can see, guys, for these two values, like this one, 2 10 to the power 5 and 2.5 10 to the power 5, we're getting exactly the same friction factors. This is very small differences, like in log scales. So when we're talking about 0.2 to 2.5 into 10 to the power 5, this Reynolds number doesn't make that much differences in the friction factors. So here we have got the Reynolds number is 2.3. This is 2.2. So we already know that difference, it was like 2 to 4, and it's only 2.3, 2.2. So that's very small differences here compared to that whole scale, like how this Modi chart is developed. Anyway, so when we use this Reynolds number again, and when we calculated the the friction factors by using this Reynolds number, like 2.2 and 10 to the power 5, when we use this Reynolds number, look, I should write it down here. When we use this Reynolds number, 2.2 and 10 to the power 5, and this epsilon over d equal 0.0012, then we got exactly F1 equal 0.0215. So that's validate our assumptions. You understand what I mean? So this is, we did same thing couple of times. So when we use this Reynolds number, and for this friction factor we got it is 0.0215, what we had earlier, 0.0215. That means this is actually confusing thing, I know. In first attempt, it's sometimes hard to understand, but I can tell you in the final exam, I will not give you a question where you need to use the Modi diagram. If you need to use the friction factor, we'll provide the values or some concrete data. So if you still need to use the Modi diagram, you do not need to do trial and error. Okay, so I will make sure that one, because I really want to make sure that okay, you know how to do that, but I don't want to, like thermodynamics or these subjects, sometimes you need to do interpolations. So if I make it complicated, you need to spend 10 to 20 minutes to do the interpolations, and that doesn't make any sense. So it just wastes of time. So I will set the question, and you do not need to do this annoying things, trial error. This is really annoying. So I'll not put that on. Okay, don't worry about it. But you must need to know it. So that's why I'm just solving this question, you see. That's why I didn't solve the question 2, but I started this one. So now, okay, let me check the chat box. Yeah, so you can use the computer softwares. Okay, well, we have the software as well for these subjects, but we're not using any software actually. But we can solve all of these things by using software. Yeah, that's true. So now we have got this value. We have got the velocity, so we can easily calculate the flow rate, guys. So once we have all of this, let's calculate the flow rate. We have done with the first part of this problem. So the flow rate, it was the velocity and the area. The velocity I got, we got 1, and the area is pi d squared over 4. It is 1. Pi diameter is 0.22 square over 4, and it will be 0.0380 meter cube per second, or 38 liter per second. So that's the flow rate. Yeah, that's the first part of the solutions. First part of this problem. Second part, well, we do not need much time to solve the second part of this problem. So yeah, we can solve it. Hopefully, we got time. So we defined this is let me check what I said earlier. Okay, we said this is point A, this is I, this is E. Okay, so the second part of this problem is, it is asking about the pumping power. So you know the pumping power, it is equal to the density, gravity, the flow rate, and the pump heads. Right, the pump heads. So what we will do is, we will actually now use, okay, I think I said this, it was point O, not A. So now I will use the energy equations from O to E. The energy equations from O to E. And you know this is PO rho G, PO squared to G, ZO. The pump heads, this is equal PE rho G, VE squared to G, ZE, plus the plus we have the friction loss here. That means F on, L on, B on, VI square over 2G, and F2, L2, D2, V square 2G. So if, see guys here, this is the friction factor for the inlet pipe. This is the discharging pipe. Okay, so we already know this friction factor F1, and this F2 we don't know. We will calculate that one. So what I can say, the pressure here, this is atmospheric pressure. The pressure at the exit, this is atmospheric pressure. So can I say this pressure is 0? Not 0. We can cancel out this one. This 2, right? The pressure at point E and point O. So that's we can cancel it out. The velocity, it is 0 here because the water is at rest here, and the elevation, it is also 0 here. So we have now the pump heads, it is equal this, the right hand side. We can say the pump heads, this is equal, VE square 2G ZE, F on, L on, D on, VI square 2G, F2, L2, D2, PE square over 2G. Okay, so we're looking for this pump heads. So we know almost everything, guys, but I think we actually don't know the exit velocity. We don't know this VE, and we don't know the F2. That's the two unknown. If we actually want to calculate this pump heads, the exit velocity is unknown and F2 is unknown. Okay, we'll solve gradually. Let's calculate the VE, the exit velocity of the pump. The pump exit velocity, like the outlet velocity. How we can do that? So that's that conservation principle, right? Yeah, so that mass conservation principle. Yeah, so we'll use the mass conservation principle for, point I and point E. That means from this section and these sections. So let's say the mass conservation principle. I will just quickly write it down like this: VI pi by 4 DI square. It is equal VE pi by 4 DE square. Okay, you know this is area and this is velocity. Okay, the first term is velocity, the second term is area. So we can cancel out pi by 4 from both sides, and then BE, it will be, it will be VI DI square over DE square. So VI is 1, DI is 0.22, and DE is 0.18. So it will be 1.49 meter per second. This is VE. So we have got the velocity, the outlet velocity. So now we need the friction factor, F2. Okay. So we already know the relative roughness. We just need the Reynolds number. And as we know the exit velocity of the discharge pipe, so now we can calculate the Reynolds number, isn't it? Yes, we can get the Reynolds number now. Because Reynolds number means, the Reynolds number, RE, this is equal the velocity, diameter, and the viscosity. Here we are calculating, look, F2, it is associated with this pipe. That means the inlet pipe. F1 is associated with this pipe. We calculated it earlier. Now we need the F2, that means the discharge pipe. So that means we need the velocity for this outlets, this pipe diameter, and this kinematic viscosity, isn't it? So velocity is 1.49, we just get it. Diameter is 0.18, and the viscosity is 10 to the power minus 6. So the Reynolds number is 2.7 and 10 to the power 5. So that's the Reynolds number. For this question, it is easier. Why it is easier? Because we know the velocity. So then we easily calculated the Reynolds number. But the first part, the velocity was unknown, so it was hard. So now by using this 2 for pipe 2, or in pipe 2 or the discharge pipe, the epsilon 2, it will be 0.26 over its diameter is 180. So just we converted it into millimeter. It is 0.18 meter, so now 180 millimeter. So this is 0.00144. So this is the epsilon, that the relative roughness value, and this is the Reynolds number. For this 2, by using the Moody diagram, we will get F2 equal 0.022. Okay, so for this 2 value, we'll get the friction factor is this. So you look here, guys, don't think the relative roughness for this inlet pipe and the discharge pipe is same, because the definition is the epsilon over d, as the diameter for both pipes are different, so the relative roughness, it will be different as well. Okay, so that we got it here, and when we know Reynolds number and this, we got the frictions factor is this. Now we will substitute the value here, this pump head. We know this pump head expressions, so we'll just substitute the value here. The pump heads, it is equal, we got BE square 2G plus Z E F on L on D on BI square 2G F2 L2 D2 B2 square 2G. So VE is 1.49. This is 2 into 9.8. ZE is 5. Is equal 5 here. F1, if I can remember, we had F1 equal 0.0215, right? 0.0215. The length 1000. Diameter 0.22. V1 is 1 squared, 2 into 9.8. F2 we got 0.022 into L2 equal 500. This is 0.18. V2 equal, we calculated just 1.49 square into 2.98. So we'll get the pump head is 17 meter. So that's the pump head. And now we have done with this problem. The pump power, it is density, gravity, flow rate, and the pump heads. So density is 1000, gravity 9.8, flow rate, I need to check it out. 0.0380, and this is 17. So it will be 633 on what?